now we are going to move on to our next panel discussion that is going to be talking about what the ideal quantum job candidate is from an national laboratories, academia, and industry. What are they looking for when they're hiring for quantum positions? And so I would like to introduce Kai-Mei Fu, who is our Deputy Director of the C2QA Center and will be the moderator for this panel. So Kai-Mei, I will turn it over to you.
Thank you so much, Diana. So as Diana mentioned, I'm Deputy Director of the C2QA. I'm not using the background. I'm hoping we can try to make this as informal as possible for this discussion. I'm also an Associate Professor in Physics and Electrical and Computer Engineering at the University of Washington, and I have a dual appointment at the Pacific Northwest National Labs. And it's my pleasure to introduce our panelists. We have Kwabna Bediako joining us from UC Berkeley today, Brian Goucher joining us from IBM, and Nathan Baker joining us from the Pacific Northwest National Laboratory. The way I want to start off this panel is to give our panelists an opportunity to briefly state what they do now and how they got to where they are in this very new and emerging field. While the panelists are giving a introduction to themselves and their trajectories, I want to encourage all the students out there to ask your questions in the Q&A. There was great questions in the last one coming up. And we will have plenty of time to address audience questions during this panel. So with this prompt, what are you doing now and how did you get there? Let's start with Kwabna.
Hello, everyone. My name is Kwabna Bediako, and I'm an assistant professor of chemistry at UC Berkeley. So I started my current position on the faculty here at UC Berkeley in 2018. And before that, I was a postdoctoral researcher at Harvard University in the physics department. That ran from about 2015 until 2018. Prior to that, I was a graduate student in the chemistry department, or Department of Chemistry and Chemical Biology at Harvard. My trajectory, maybe, I don't think it may sound unconventional, but I don't think it actually is when you hear some other stories. So as you can tell, I started out in chemistry, and I always had a deep passion for renewable energy storage and energy conversion, thinking about the climate crisis and particularly trying to discover ways to make better use of renewables, solar energy in particular. So my interest in this area, reaches far back to, I think, maybe late in high school when I started learning about some of these possibilities for taking advantage of solar energy. Anyway, so that's what I got drawn into as a graduate student. And I started out at MIT, and then my group, the research group I was in, moved to Harvard, and so I finished up there. Then when I finished my PhD in inorganic chemistry and electrochemistry, I was sort of looking for my postdoc for a slightly different challenge, exposure to a different field, and I had always been really interested in condensed matter physics and low dimensional systems, and so I was thrilled to get an opportunity to join a lab at Harvard in the physics department, and so I found that was a terrific experience. When you go into a different field, it's like going to a country with a different language, and so once you're immersed in it, you have a little bit of that. It's almost like a culture shock, but that's how you're really able to sort of learn the language, right, so to speak. And now my group sort of works at this interface of thinking about quantum systems, quantum materials, but also about energy. And I think there is an important interplay or important work to be done at that interface. Oh, I should say, before my graduate studies, I think this is quite relevant. Before my graduate studies began, I actually worked for a year in industry with a Honeywell company called UOP in one of the suburbs of Chicago. So I got some exposure to what industry, the chemical industry was like, and I really enjoyed that experience as well. So yeah, so that's a little bit about my background, and I'm happy to answer any questions as they arise.
Thank you, Kwabna. Let's now hear from Nathan Baker from Pacific Northwest National Lab.
Hello. Well, I'd like to start by apologizing for my video camera. I'll blame it on technical error, but it's actually user error. Don't tell anybody. So I'm happy to be here. So my name's Nathan Baker. I'm a laboratory fellow here at Pacific Northwest National Lab, and I'm also a faculty member in the Department of Applied Mathematics at University of Washington. So my trajectory is actually fairly similar. I started in chemistry for my graduate studies, and I had a wonderful advisor who also encouraged me to find a second advisor in applied mathematics. And so I kind of moved down both tracks at the same time. After graduate school at UC San Diego, I looked around and I really wasn't sure what was next. I had a lot of encouragement to continue in academia, so I did that for a while. But several folks also planted the seed that the national labs, in particular the Department of Energy national labs, were something to keep in mind for the future, and consider that as another maybe turn in my career at some point. So I spent 8 years in academia at Washington University in St. Louis, actually at the medical school in a preclinical department of biophysics and biochemistry. And then that sort of echo of the advice that the national labs are a great way to explore more applied interests, to do service to your country, to support national security missions. That echo just got louder, and I started looking around at the labs and moved to Pacific Northwest National Lab about 11 years ago. I'm really excited about this panel because for at least 10 of those 11 years, I was promoting the importance of quantum information sciences at the national labs. And one of the questions I always had, either as a hiring manager or talking to other hiring managers, is, well, where do we hire? What does the right candidate look like? So I'm looking forward to exploring that question during this panel. That's it.
Thank you, Nathan. And our third panelist from industry, Brian Goucher.
Hello, my thanks first to C2QA for having me here. I feel kind of honored to be among such a esteemed group. My area today that I have charge of is experimental quantum hardware systems and architecture here at IBM Research in Yorktown. My team pretty much focuses on the connections between novel gates and future control electronics, as well as the design tools for both our researchers and our clients. My team explores the next generation quantum gate hardware, and we try to do that in a scalable way, tying together all of the physics and basic design automation and emulation and validation, as well as structured experimental analysis in the lab. I had kind of an interesting trajectory, sort of unusual. I started here some 20 years ago in wireless communications. I started a group here doing wireless for things like you might find in your computer, IEEE 802.11 and .15 wireless systems, and helped to create all the systems that IBM sold in their ThinkPad and then Lenovo computers. Then I moved on to wireline communications, applying similar principles for our embedded processors and chips, and over into artificial intelligence as applied to smarter energy, like the integration of renewables into our electric grid, the simulation and optimization of that grid at both local and regional scales. And then I moved over into the quantum space and applied some of the microwave background that I had into the custom electronic development that drives all our quantum systems, and doing that at both room temperature and at cryo temperatures. And now I'm looking at the gates that I was mentioning earlier. So I'll leave it at that.
Okay, great. Thank you so much. So one thing that I noticed as I listened to these trajectories, some people said theirs are not too different, or some people said they're quite unique. But one thing I noticed about all three of you is, at least from my vantage point, you have done very different things over the course, whether going from chemistry to physics, going from an academic institution to a national lab, going from one technology to another technology and another technology. So I want to open the floor and ask you, what enabled you to be successful in being able to pivot and do so many different things?
I'm happy to jump in on that to start with, just to open it up a little bit. But what I found in my career, and not so much in the school, but I think people who are able to communicate sort of a vision and set the stage for what is important for us in the future, and communicate that in a compelling enough way that it excites all our researchers, our students that we get many of here, to come in and join us on that journey and to create that vision. Also to find ways to fund it. I'll tell you, industry isn't so much different than academia in terms of having to go out and get funding to make our work a reality. So we spend a lot of time in doing that. And we also have to build, we'll call it dog and pony shows, demonstrations of potential material that we can do now that actually underscores the importance of doing the research that we're trying to do. And so in other words, it's really building strong teams and collaborative networks with very diverse skills and people, and those people being very good at problem solving in a number of areas.
I echo all of what Brian said. Those are really essential skills. Communication is key. There's another piece that I can only describe as embracing imposter syndrome, right? You get a degree in one discipline, but often the most interesting problems require taking a risk and moving into fields where maybe you didn't get your degree in, but you've done your research, you've read the literature, you've tried to get up to speed and learn as much as you can, and at some point you just have to take the plunge. And so, if you're well sourced, if you've made the effort to do the background work, to get to know the field, to attend the relevant conferences, and to build the right collaborations, maybe you're not an imposter anymore, and that imposter syndrome is holding you back, and you just embrace it and you jump into the new field. And I see a lot of that in quantum, where there's so many areas adjacent to quantum information sciences, or maybe more accurately, there's so many areas that comprise quantum information sciences that you always have to kind of reach over into the neighboring field and borrow whatever's useful. So that willingness to just move back and forth, along with the work to make sure that you're not you're bringing the right skill set to it, I think is another really important ingredient.
Yeah, I don't know if I have too much more to add to that. Those are, I think some excellent advice that, I certainly wish somebody had told me some years ago. But I also found all of this to be true. So I think developing your ability to communicate concepts in fields in which you are the expert or an expert to others who are not in that field, okay, is very, very important, as you've heard. And in a sense, sometimes expanding into a new area or stretching yourself in a new area is one way to develop those communication skills. Yes, it's true that some people are, seem to have sort of a natural sort of talent or gift for speaking, but you can also practice and improve and learn some of those skills yourself. So some of it is also acquired. And so scientific communication is one thing, and it's something that you can, get better at. And one way to do that is to force yourself to explain, concepts to people in other fields. And you only get that to happen if you put yourself in those situations where you are sort of the new the new person in that room. I like to think of it as a willingness to be the dumbest person in the room. I certainly found that when I went from my PhD in chemistry to a physics lab, suddenly all of these skills I had learned and all this jargon and sort of the language that I had built up, in my previous lab, didn't necessarily immediately translate to the new one. So but I found that to be a refreshing experience, and then I learned new things in that process. And so being willing to be that person who's sort of the newbie, and then doing sort of the homework, right? Reading very, very deeply into concepts that you realize, wow, this is an undergrad concept, but I actually don't understand it. And so then you dig in, into that, because that's not your background, right? And then being willing to ask questions, not being, not being afraid of of sounding silly, in that new environment, and just asking fundamental questions. And then doing your own work also to try to understand these concepts. I think those are very, very important. And and of course, I think what I've said just sort of reiterates what you've heard from the other panelists. And I can't emphasize those enough.
Thank you so much. So there's this theme among you that you're very willing to learn new things, go into new areas, be brave, be able to be uncomfortable, and then do the hard work to catch up. It's interesting that we haven't heard very specific skills related to quantum information. So maybe opening this up, are there any specific skills related to quantum information, or following Nathan's comment, he said that there are many areas that comprise quantum information sciences. Could you, and I'll include quantum materials in there as well, could you elaborate more on the different areas of study and expertise and domains that contribute to quantum information?
I'll jump in a little bit on that one. In my area, in my team specifically, I have physicists. We're looking at superconductivity, superconducting qubits, cavities, circuit QED, quantum optics, open quantum systems, quantum circuit theory. The basic principles of Hamiltonian application of those. And as some other people have mentioned, even mechanical design, layout, programming, and simulation of systems, all are key to making our day-to-day life a success and our business a success. The ability to do multi-physics modeling and tools, general tools like Sonnet, Microwave Office, ANSYS, ADS, Cadence, AWR, all of these are used by our entire teams. And then there's the RF and microwave skills, right? And part of my background is there, but RF design and simulation and test. High-speed digital design, we're building ASICs, using silicon technology that made up to our qubits, looking at novel RF circuit designs and PC board designs, all the tools that go along with that, from numerical modeling and analytical skills. How do you test these things, right? We have teams of people in my area looking at room temperature and cryogenic tests. Again, superconducting electronics as it relates to quantum computing, looking at a mastery of cryogenic systems, dilution fridges, how they operate, HPDs, Genesis fridges, probe stations. We need people with all of these skills in order to get into the lab, test lots of different circuits, pick the best of those and put those into a system, and then test that system against all of the metrics that we've put together, and then run those with the software that we've developed. You'll see Qiskit as one of the platforms that we have developed and make available for free to folks to use, but it's really Python-based software for people with software programming as well as a physics background and the knowledge of quantum into that area, and you can see tutorials there. But I'll stop there.
That's a hard list to follow. I think you hit most of it. I'll tell you where we've seen interesting opportunities of folks kind of crossing over into quantum. certainly material science and chemistry. There's, unlike classical computing, we don't really know what comprises the fundamental unit of computing. There's so many choices out there for architectures and for the materials that make those architectures that you almost always need a material scientist, an engineer, or a chemist to help you understand what's the next system you should be looking at. And so that's an area where we're always looking for talented folks who are willing to make the jump. The second is maybe a little more unique to the national labs. We have a lot of folks with background or no pun intended, in very low background detection, trying to understand, basic problems in particle physics, or applying those to problems in treaty verification and non-proliferation. That type of that ability to work in systems with very, very little tolerance for outside interference and noise translates extremely well to quantum information sciences. And so that's another area that we draw from. And then, of course, applied mathematics, computer science, the folks who know how to do co-design between an application and a hardware, that those are all just essential.
Thank you.
Yeah.
Oh, please go on.
No, I'm just going to say, I think for fundamental research, in this area, there is indeed like a wide array of approaches and backgrounds that are needed, right? As you've heard. And if you even take a look at, in just the previous session, if you look at the researchers, that are involved in those centers, you'll see that they, cover, an array of expertise from synthetic chemists. So those could be solid state chemists, or chemists who make molecules that could act as qubits, physicists, and these could be physicists who are interested in sort of electrical transport or RF measurements, or they could be ultra fast physical chemists or physicists, and so and then engineers. So I think that there isn't necessarily, at least sort of on the fundamental side, a particular tool set that is needed. I think you can bring your particular area of interest and expertise to bear on tackling some of the most important fundamental basic science questions that we still need to solve to advance this particular field.
Great, thank you. So we have some specific questions coming up in the chat. For example, how can a mechanical engineer contribute to quantum computing? How does someone transition into quantum from computer science? I might just take one of them in terms of mechanical engineering. I know that at the University of Washington, we're hiring in mechanical engineering in quantum, and the department was very excited about control systems and mechanical systems. You can actually have quantized mechanical motion that can be part of the quantum information processing system. And then there's the larger kind of broader question in the chat that says, how do you build the relevant portfolio? So maybe keeping this question kind of open, how does someone who is now getting an undergraduate degree in a particular engineering field, how do they get their foot in the door in this exciting new area?
Well, I'll start, particularly because it pops up in other questions in the chat as well. Internships are a great way to get started. And I think, particularly in the labs, also in industry, interns are our lifeblood for getting new ideas in the door, for training people in areas they haven't been exposed to before, but also it's a pipeline to hiring long-term staff as well. So if you can find opportunities for internships, and the previous panel talked about all sorts of opportunities, and there's some in the overall chat as well, then definitely take advantage of them. There also are internships at the labs that are tailored to people with specific backgrounds, and we do outreach to the military and some of the national security communities. And I'm always happy to talk more with folks in those communities as well if they want to find out specific opportunities at the labs. But I think the short answer is internships.
I just want to jump in and underscore what Nathan just said. Internships are also our lifeblood here. I look at that as my pipeline. We've had 3 interns this year and tried to make offers to 2 of them, really solid folks. And they come in with, in this case, PhD level backgrounds, and spent, in one case, 2 summers with us and designed real hardware that gets fabricated and built and put into our systems. So they're both, beneficial for their own PhD thesis and work, as well as being useful in what we're doing. I can't think of a better synergy than that for both us and for them. And we look at everything from undergrad to graduate level here. And there are order 50-ish in the quantum space here at IBM Research that we bring in each year. So there's lots of opportunity. It's competitive, but it's a great way to get your foot in the door, as Nathan was saying as well.
Kwamna, how about on the academic side?
Yeah, research of sort of any flavor, whether it's an industrial internship, national lab internship, or academic research, I think is at the core of sort of building your portfolio, as the questioner put it, in any particular field. And so in academic, and sort of the academic approach as well, if you're an undergraduate and you're interested in graduate school, research experience is one of the most important parts of your application. And so, reaching out to faculty at your institution, looking for internships at national labs, if they're available to you, if that's available to you, or even industrial groups, those are all going to be very, very important in terms of getting your foot in the door. And one of the things the reason research is so important, it isn't necessarily because what we're looking for, in our graduate admissions, specifically speaking from that perspective, it isn't because what we're looking for is that you've built up a set of technical skills in a particular area. Because we know that you will develop those skills in your PhD research. It's more what we're looking to assess is whether you know what research involves, right? You know what the process entails. That it entails probably, almost, I hate to break this to you, but a lot of sort of frustration and failure, because you try something, you have an idea, you test it, it doesn't work. You try something else, you test it, it doesn't work. And so the persistence and the problem solving needed, sometimes you want to do an experiment, but you've got to build the tool so that you could actually do the experiment you want to do. Or maybe the tool that you're going to use breaks down. Can you solve the problem? Can you figure out where that instrument is not working, and can you fix it and then be able to do your experiment? It is that sort of problem solving, the critical thinking needed, the persistence, the resilience that you need to develop to sort of dig and dig and dig into a topic area to become an expert. And we want to just establish that that you at least have some appreciation that this is what it means to do research, and so being able to show that, hey, I've done some research in one context or another, gives us that confidence that this person coming in understands what it means to be a researcher, and that they have this resilience, this persistence needed. And so I accept graduate students into my group who have no background in the area that we're pursuing, but what I do see in them is an appetite, a desire to learn that stuff and to become, the experts in that area. And then they can take some classes to give them the basic foundation, of course, but also I know that over the course of their studies, they are going to keep at it, work at it, and become the experts. And so that's what we're looking at when we're evaluating these applications.
Great, thank you. And then, I imagine that internships, research positions can be incredibly competitive. Could you describe what students should be doing, or even if someone already has their degree and they want to go into this field, what types of opportunities should they be pursuing, or personal projects or research that could help gain the skills that you're talking about, if to maybe get that internship, or maybe get the job without being able to be one of the few that got the internship?
Not an easy question to answer, but I'll add a few comments. One is, again, not necessarily strictly speaking something you learn in school, but networking is a key part of what we do. Going to the conferences, presenting papers, get you some public facing information, and starts building a network of people that you can call on when internships come up. Often when you're at a conference, even virtually, you can make inroads to get to something that may make sense for you. And through those internships, you look at where you amplify on skills and where you should be working or focusing more, and understanding better what the industry is looking for, or what academia is going to need. I've had 5 of my own employees go back to academia and become professors. And so that it's a two-way street, and they send their interns back to us. So I think that kind of thing works out well. I'll stop for a moment there and let Nathan or Kwambi.
I guess I'd just say +1 or something. I agree. The self-starter aspect of and the initiative that students show also can help be a defining factor in being selected for an internship coming in. And this applies not just to quantum, but really any area. Did they do their research not only on the area, trying out tutorials for Qiskit or other resources out there, demonstrating, with their own GitHub profile that they're playing around in this space if it's computational. Those are all important, but also showing that, you've looked into the institution, you're applying to the lab or the company or the academic group for a specific reason. That can be really important if an institution's getting bombarded with many applications, as is the case in hot fields. The ones that say, I'm looking at PNNL because of your work in whatever low background radiation detection or things like that, that really can set an application apart.
Okay, great.
I'm just going to say I underscore that in a big way. What Nathan just said, if you came in and with experience in the exact tools that we make freely available, that's going to make a huge difference if you can talk and converse in the same language that we're using here. I think that's really a really important part.
Okay, great. So something that's come up in the questions as well is, what degree do you need? Master's degree, okay? Do we need a PhD to be in this field? And just an undergraduate degree?
From an industry perspective, we have everybody from undergrads to graduates. We have most of my team are PhD level folks, but we also have both master's and bachelor of science folks here. We need people in the lab, hands-on from a technician standpoint, who really know the hardware and how to get something operational from the get-go. And that doesn't take a PhD. We get a lot of people across the spectrum. We're very vertical, from all of the device materials processing all the way to the top of the stack, from software to the experiment and analytics of data. So it's really across the board.
Yeah, I agree. Quantum information science is, again, it's so diverse from with respect to discipline. It's also very diverse with respect to terminal degree. And I would say in this case, the labs probably strongly resemble industry in that there are people of all degree disciplines and also, degree titles, whether it's a bachelor's up to, postdocs and other advanced degrees that contribute to these missions. There's really a spot, I think, for everyone.
Okay, thank you. So another question, we'll move into some specific questions for some specific panelists. Nathan, you mentioned needing material scientists and chemists in order to choose new systems for qubits. In those cases, are these scientists involved in choosing known materials that can be newly applied or synthesizing completely new materials? Are there opportunities in support for basic research into materials?
Oh, absolutely. And on all fronts. So while it's always nice to be able to go from sort of cradle to grave with a material to a device, that I don't know the statistics for how often that actually happens. And a tremendous amount of work is spent at the basic research phase, not only trying to understand what's possible in the space of new materials, but also just understanding, reconciling performance or other properties, quantum properties of the material with their underlying structure and composition. So that has, that can be as basic as applying state-of-the-art quantum chemistry and materials codes to simulate these, to doing the synthesis of the materials and characterizing them, to trying to close the loop and make it more of a design process. So I'm not sure if I answered the question, because the answer is sort of yes to all of the above. There's a huge basic research need, but there's also a need to take materials that have been identified and try to bring them to a point where they can become useful devices.
Great, thank you. For Brian, how much scope is there for theoretical research in quantum computation and quantum materials in companies or in industry?
There's actually a lot going on. We have two teams. One of my folks, David Mackay, here is got a team of folks on theoretical applications of quantum, as well as a team in Almaden, California, who work in that space as well. So there are two separate groups of people, and they both live both West Coast and East Coast, heavily involved in that. We were looking at all the way up through applications of theory into solving real world problems, looking at drug discovery and how we might do that, the basic travel salesman problem and max cut problems. We're looking at much better ways of introducing quantum computation along with hybrid systems that make up both what we think traditionally of high performance computing embedded with quantum computers and theoretical applications there.
Okay, thank you. I think this is a question for all three of you. Is there a path for more senior researchers greater than 5 years out of their PhDs for going into quantum information and quantum materials? And as a caveat, I think all of you are more than 5 years out of your PhD, so I think there is a path, but maybe you can describe more paths that you've seen.
Okay, so no one's talking, so I'll jump in. But yes, absolutely. We hire what we call early professional hires, sort of right out of school, and that's kind of the internship path. But we also bring in experienced professionals who have a lot of experience in what we're doing today. They may not even be doing necessarily quantum computing, but have that background in their training. And they can come in and join us as well, as long as they're showing both the passion, the basic knowledge, and desire to move into this space.
Yeah, likewise. Oh,
go ahead.
Sorry. I was just gonna say, yeah, I think there are pathways. I think if you have a PhD, then a postdoc. If you would like to pursue a career in academia, then a postdoc is one of the next steps. It is quite challenging and competitive to get postdocs, and it is probably true that the further out you are from your PhD, the more challenging that might be to re-enter at that point. But it does happen. It can be done. I think reaching out to faculty whose research you find really interesting. I think articulating very clearly in your letter, why you are interested in this area, giving a little bit of background, sort of explaining what you've been doing in the intervening years, and articulating why that actually makes you an asset, why that actually gives you perhaps an upper hand compared to other applicants, things like that. I think you can make a compelling case for that. And so I think, yes, there are pathways through a postdoc to come back to get into academia, for instance. But those, I have to admit, those do become increasingly difficult as the time from your PhD progresses.
I'd like to just add to that, since sometimes national labs look like a superposition of academia and industry. All of the above applies. I also see a lot of senior scientists reinvent themselves, again, because there are so many fields that are adjacent to quantum. They either get drawn in the way Brian described, that you need to pull in somebody, of a particular skill set, or, a faculty member or a senior scientist at the lab may just say, hey, this looks really cool, and I see a way that the things I've learned in the past could apply to this area, and I'm going to take a stab at it. And so we see that a lot in computer science, where the models you use for programming languages need to be adapted to understand to describe quantum algorithms. We see it in material science, where folks realize that say certain structures they'd looked at or ways they'd characterize materials are very useful for looking at materials in quantum, and so on and so forth. So I think it's you're never locked into a research direction for the rest of your life. There's always an opportunity to pivot and maybe, if not completely jump tracks, you can at least start to angle in a different direction.
Thank you. So we only have a couple minutes left before closing the session. I just want the panelists should be able to stay on and help answer the many, many questions that are still left in the Q&A. So I encourage the panelists to stay on. In this last minute, is there anything a panelist would like to say to the students listening for how to be successful in a career in quantum information and materials?
Well, it's a great time. Oh, sorry. Go ahead.
No, go ahead, Nathan. No. Go for it.
It is a great time to be getting involved in this field, because there is no such thing as a quantum scientist or an engineer right now. There's just an awful lot of routes to contributing to the field. It hasn't been codified or maybe ossified. It's fluid, and so it's just a great way. I've looked at the different, we see chemical engineering, math, computer science in the questions here, cryogenics, microwave, and the answer is all of the above. There's so many ways for folks to get involved in this field, even from non-traditional backgrounds. IBM has some really interesting work that they've done with their blogging. Microsoft has work they've done with bringing more of the STEAM-like approach with arts in this. So it's really a wide open field, and now's the time to be getting excited and getting involved in it.
and I'll just add to that, I think what Nathan said is spot on, but I couldn't think of a more exciting time for both industry as well as academia to get involved in this space. You're sort of on the ground floor in a way that's inventing the future. And getting involved is as simple as building on the network that you have and making those contacts. Joint publications and papers are great opportunities for both students and for experienced professionals to get their names out there. And participating in conferences and meeting people at conferences are another great way to move forward in that network and create the opportunities that everyone might be looking for.
All of the above. Yeah, find the point of intersection between what you're very excited about and you know, the web of opportunities in and approaches to this very, very broad field, and there's no one particular approach to it.
Right. Well, thank you so much, Brian, Kwabna, and Nathan, for joining us. So this ends the panel session, and we will be following up and answering the Q&A in the chat. Thanks.